I'm Eric Lerner with LPPFusion, and this is the first of a new series of videos, which are dialogues on cosmology, the question of the reality of the Big Bang, expansion, and what are the alternatives. So the first guest we have is Dr. Rajendra Gupta of the University of Ottawa. And Dr. Gupta made headlines worldwide back in July when he published a paper that indicated that the universe was not 14 billion years old, but 27 billion years old. And perhaps more significantly, that his hypothesis was that the redshift was not entirely due to the expansion of the universe, but was partially due to what has been called historically a tired light phenomena, something that happens to light as it travels through space. So basically, the format of this dialogue is that we're going to start with my asking Dr. Gupta some questions, and he'll ask me some, and then you all in the audience can ask us both some or make comments. So to start out, basically, I'm going to hand over to Dr. Gupta and basically ask, well, what exactly was your paper about? What was all the fuss about? So let me.
Yeah, I will try to answer it. Actually, I didn't expect that kind of stir or fuss or whatever about this paper. It was a very simple paper. I had seen something while reviewing a paper in late last year that used the tired light theory to resolve the problem of angular size of certain galaxies observed by James Webb Telescope at cosmic dawn at very high Z, maybe about 400 to 500 million years after the so-called birth of the universe, the Big Bang. So that's gave me an idea. I have been dabbling about this kind of thing for some time. Tired light theory I had used in the past in explaining something partly, but it was not very satisfactory at that time. But that gave me an idea that if James Webb Telescope observations could really be explained with the tired light theory, but perhaps some other things are not as well explained, just like fitting the supernovae data. If we want to supernovae type 1a data, if we try to fit with the tired light approach, then at least the way the data is presented in Pantheon Plus or Pantheon data set, it doesn't fit very well. Actually, it doesn't fit. And it gives very high chi-square value, so it doesn't fit. But at the same time, lambda CDM model does fit. So I thought of why not we combine the two? And combination comes from the fact that the distance traveled, whether it is expanding universe or the tired light, is the same. So you can use the same distance in both the approaches and hybridize these two and come out with a new model, which you could call the hybrid model. It could be lambda CDM plus tired light model. That's what I tried, and it fitted the supernova data well, as it's supposed to, this hybrid model, but this did not fit the angular diameter observed by the James Webb Telescope. So what do we do next? But I have been working with the varying cosmological constant concept, not cosmological, sorry, varying coupling constants approach for some time to explain certain observation or just to think what it could be, because Dirac had predicted such kind of variation, and all the observations, all the studies which were done using that came out negative, means against Dirac predictions. But then
Dr. Gupta, could I interrupt just
certainly,
for clarification for our audience? Could you explain what you're referring to by the coupling constants? Could you give
coupling constant,
examples that people are familiar with?
yeah, coupling constants are the constants like the speed of light, the Planck constant, the gravitational constant, Boltzmann constant. These are the ones which relate the somehow the energy relations between the different particles and different bodies. So this is the one which are Dirac had predicted the variation of the gravitational constant and the fine structure constant based on his large number hypothesis. And I don't want to go into detail on those things, but really to keep it short, I would say the coupling constant variation, I found they are not really independently varying, but there is a correlation in their variation, and they are correlated through a single function. So if that function is not varying, then none of the constant is varying. If that constant is varying, then all these constants would be varying. But all the studies I have seen were done assuming all the other constant and only one constant varying, just like G, for example, gravitational constant. So that automatically will not give you any positive result because you are constraining the variation of this function which relates them. But I found that relation, and then this is what I fit in the new approach. I say, okay, let me allow these constants to vary, which enter in Einstein equation, and eventually in some other observation they enter as well. Let's allow them to vary through this function and see what happens. So it changes the Einstein equation, and then when we try to fit the data with this hybrid model, this varying coupling constant model, you might say, or covariant coupling constant model, which I called it, because they are all varying together. So with that one, and coupled with the twilight model, and we find we could fit the supernova data as well as the lambda CDM model, as well as we were able to fit the James Webb data. So that was very encouraging, and then I thought maybe we should publish it, and that's what I published. One problem was that it was giving the age of the universe quite high, but I thought that's okay, it gives that high. I never thought it is a big deal. It was published in the monthly notices of the Royal Astronomical Society, and when it came out, I just informed as a routine thing to my media relation people that this paper came out, filled out a form, and that is when this was released, and they caught this very important thing that taught the age of the universe part, and that caught the attention of media. And I think, to me, it appears very embarrassing that suddenly something relatively trivial got the attention of media. So that's the all the story about it.
Well, let me ask you, I mean, in putting forward this hybrid model, in your paper, you were saying that the JWST data does not correspond to the predictions of the existing model, what some people call lambda CDM, or what they themselves call the concordance model, borrowing a term from religion. So what would you say, just briefly, in layman's terms, are the main contradictions you see between what JWST has observed and what were predicted by the existing concordance model?
Actually, there are a few things. The angular size is one thing, but then when they determine the mass and shape of these galaxies, they appear to be almost as mature as the galaxies we see around us, but we're much smaller. A much smaller effect comes because the way distances, angular diameter distances, angular distance is measured, or the distance of angular diameter distance, what they call it, is the way it is determined in a model. Now, in their model, in the existing concordance model, it gives a different angular diameter distance than in the new model which I have proposed, even when we include the tired light. That's significantly different. And that made the difference in terms of the size. So angular diameter, they interpreted as a smaller size. Angular diameter, we interpret with our model to be 10 times, about an order of magnitude larger than they interpreted. And then these galaxies started to make sense, sizes of these galaxies, physical sizes.
But there were other things, other predictions that have been wrong about the concordance model, right?
Of course, there are so many things we know they are wrong, but I think from the James Webb Telescope point of view, the predictions which they were making about the size of the galaxy, the masses of the galaxies, and all that, they were very different than James Webb observed.
Right. Now, did you, prior to the James Webb Telescope results, did you publish predictions about these sizes, that they would be, that the angular sizes would be smaller than the concordance model predicts? Or is this something that...
No, I did not predict that. This came out of one of the paper which I had reviewed. And in that paper, I saw that the tired light model was able to fit that observations, JSW observation size, angular size observation very well. That gave me an idea, maybe this tired light model should be combined with the expanding universe model to fit both the things, the supernovae data as well as the JWS data.
Well, there's been, of course, a pretty active response from the cosmological community to your paper. To be frank, we're really responding not to your paper, but to the public media, whatever we could call it, kerfluffle over the change in the age of the universe. But I did notice that one of the criticisms, and I'd like you to respond to that, was that your model, which involves the expansion of the universe, as with the concordance, the change in coupling constants, and an unknown tired light phenomena, has too many free variables, and that you basically can fit almost ex post facto, you can fit almost any set of data having so many free variables. What would you say to that critique?
Actually, I will say they haven't read my paper. There are only 2 free parameters in that. Only 2. Same as in concordance model. So I don't know what they are saying, because in the concordance model, there are two parameters, which are the Hubble constant H0 and the lambda constant itself, given the dark energy. Okay, so
Oh, really? They have more because
no,
the
I,
dark matter is another free variable.
but dark matter, if we consider a flat universe, then dark matter plus the dark energy, dark matter itself is not required for the fitting the James Webb angular size data or supernova data. All you need is total matter. So total matter plus the dark energy related energy density, total matter density and our density together are fixed. So as a result, you need only one of those parameters to fit that data.
Mhm.
So that way, same way, in our case, what we don't need lambda as a constant to be fit or related energy density parameter. We need a parameter which of the function which correlates the coupling constant that has one constant. So there are only two constants in this one. So I don't know why they are saying multiple constant, where from they got the idea there are multiple.
Well, let me ask you, because perhaps I didn't understand your paper either. I mean, it seems that you do have a free variable in the sense that the balance between the tired light redshift and the expansion redshift, or equivalently, what the age of the age of the universe is since the Big Bang, that is something that you don't derive in advance, but you fit to the data. Isn't that another free variable?
No, it is not a free variable. Why it is not a free variable? Because the distance traveled by the light is the same. Expanding universe, it gives the same distance as the tired light. Tired light is traveling the same distance. So that way we constrain the two distances, distance determined by the tired light and the distance determined by the expanding universe. They have to be the same. So that constraint then removes any extra parameter. There is no extra parameter for that. We are not adjusting the ratio of this, how much is the tired light and how much is the expanding part. It comes out automatically from this. So there is no extra parameter.
But I'm a little confused here, because if the distance traveled is the same, why is the angular diameters different?
Because angular diameter will become different because the distance is now being reduced. Because if it is tired light, if suppose you take tired light, if it is the only factor which is contributing to, okay, let me give an example. You have a tank, a car full, which you are driving, which has a full tank, okay, of gas. How far you can go? It depends on what is there are two factors which are creating using your fuel. One is the friction, and second is the drag of the air around it. And both, you are still traveling the same distance. So they are the two factors which are contributing to the use of the fuel. Similarly, thing you can say about this phenomena. You are still traveling the same distance. Light is traveling the same distance in expanding universe or the other. So you can definitely say that you can equate those two distances, and that way you can constrain the two.
Well, let me ask another question, which is, why did you, I mean, I think you and I totally agree that the JWST data and many, many other sets of data that have been derived cosmologically conflict with the predictions of the concordance model. In fact, I would say conflict with the predictions of any expansion model. Why do you feel that expansion, the hypothesis that the universe had an origin in time and that space is expanding, should still be accepted? Why should we not reject that hypothesis and attribute the Hubble redshift relationship? Light shifts to the red and as distance increases entirely to a tired light mechanism.
I believe there have been historically reasons to adapt two things at the same time to explain certain phenomena. For example, there was a time at the time of Newton, he proposed the corpuscular theory of light. And it prevailed for about 100 years, but then some of the observations, diffraction patterns and all that couldn't be explained easily with the corpuscular theory, and the Huygens and others, they proposed the wave theory of light. And then this was very well accepted, everybody loved it, and that went ahead until some of the things which were found were not able to explain the emission of electron from the surface when the light is following photoelectric effect, could not be explained by the wave theory. So Einstein resurrected the corpuscular theory and said, okay, that could explain. But really, we eventually found the light has both the properties. In fact, every particle has the property of being wave-like as well as the particle-like. So, that is, to me, having a model which has the characteristic of both, there's nothing wrong. That expanding universe, and we have, in addition to that, we have some characteristics of the steady-state universe. Like some of the things you yourself have proposed, they don't have to be exclusively in the steady-state universe. They could still exist into the expanding universe. So I think there's no harm considering these things to coexist.
Well, certainly there's no harm, but obviously history has counterexamples. The example of presumably all familiar to all of us of Tycho Brahe, who in the battle between the geocentric universe of Ptolemy and the heliocentric, sun-centered universe of Copernicus, he attempted to merge them by saying, well, yeah, all the planets go around the sun, but the sun goes around the Earth. And he basically tried to say, well, these are equivalent. And of course, along came Kepler and proved that a conclusion Kepler was not very comfortable with himself, but he did stick to it, that everything is going in ellipses, which made it impossible to maintain Tycho Brahe's universe. So there are counterexamples. But I think that the key criterion that we've sort of emphasized in this series on JWST is, do theories predict observations correctly in advance? Because after all, that is the usefulness of science to us, is ability to predict things that will happen in the future under certain circumstances. If we do certain things, if we make certain observations. And the key thing that, to me, is the question is the universe expanding, yes or no? It pretty much is either expanding or it's not. And I and my colleagues, Ricardo Scarpa and Renato Falamo, have spent a lot of time on this angular diameter question. And we showed that we could predict both the HST results up to a redshift of 5, and before they were observed, the JWST results we publicly predicted would fit the linear relationship that the distance to an object is simply proportional to the redshift, and that therefore its angular size, as in ordinary space, non-expanding space, shrinks in inverse proportion. And those predictions are correct. I mean, we haven't published a new paper, but we're in the process of it. But the linear model, which has no free parameters, does fit the data. I mean, your compound model, which was inspired by this data, as far as I can see, and correct me if I'm wrong, you did not actually look in statistical detail at the data and see what the fit was, what the chi-squared, the distance to the fit was. Did you? I mean, I didn't see it in your paper.
No, I did not. I did not do that. The same kind of thing which I did with the supernovae. That I did not do with this one, no.
Because, I mean, as I say, we haven't published this, but there does seem to be a really big gap between the predictions, as I understand it, from your theory, because your theory does include expansion. You again have a curve in which the angular diameter reaches a minimum and then curves upward again, while the linear non-expanding universe theory is a straight line downward, as it is in ordinary space.
That's right.
And I can say, because this is a mathematical result, that at a redshift of 10, there's a pretty substantial difference between these two predictions. The predictions differ in size by a factor of about 5. So, of course, as you say, your predictions for angular diameter are 10 times larger than the predictions of the concordance model, but they're 5 times smaller than the non-expanding model. So that's pretty substantial, because as I say, we've done only a preliminary examination, but the results do fit the non-expanding model, which means it's a pretty substantial gap. It's a factor of 5 between that and the hybrid model. I mean, what is your response on that?
Actually, I should refer it to the one of the paper which I was referring to is by Nikita Lovagin. That was published in I think in December last year. In that one, he has considered a linear model as well as the tired light model, and at least in that paper, he showed that the linear model is not as good a fit as the tired light model. So that's all I can say. That's what I had studied. I have not studied in great detail all these things, because when I developed this new model and I found interesting result, I thought I should publish it, because the other paper which I am referring to, Nikita Lovagin paper, that did not, when I took that model, it did not fit the supernovae data well. I knew that will not be acceptable that way. Only the JWST data that was fitted by that model.
Yeah. Now let me just clarify a few points before I turn the questioning over to you. The model that I've been working on for decades, and my colleagues have been working on, is not a steady state model. That's the model of Dr. Fred Hoyle and his colleagues, which made the assumption that the universe is not evolving. We don't make that assumption. We make the opposite assumption, that the universe is evolving as we see evolution all around us in the galaxy, here on planet Earth, in our own society, but that it never had an origin in time. So it's been evolving indefinitely. And as you move forward in time, the evolution increases, the rate of evolution increases. So I just wanted to make that point. We are not talking about a steady state, a model, but a non-expanding model. Just like here on Earth, the Earth hasn't physically expanded, but it looks a lot different than it did 4 billion years ago. The other thing I just want to clarify for the audience is that, and again, correct me if I'm wrong, in the tired light model, you're referring to a model that mathematically predicts an exponential decay in the energy of light, and therefore a logarithmic relationship between redshift and distance. While when we refer to a tired light model, we refer to a model in which a presently unknown process creates the observed linear relationship between distance and redshift. So I just want to make that clarification that unfortunately, astronomy is littered with terminological inconsistencies. So you have to define pretty well what we're talking about. So right now, I'd like to turn the questioning over to you. Do you have questions that you would like to ask me about the work we've been doing in the same field?
Actually, yes, I have the questions which I'm trying to answer, and these are I can reflect back on you and request you to answer them, because to me, one of the interesting thing might be to create a hybrid model with the linear model you are presenting or you are suggesting, and with that, including the expansion. What happens in that? Is it any better? What the age comes out? Maybe I would do a little bit of back of the envelope calculation tonight to really find out how it fits. You know, might be something interesting. But I would love to hear your comments about about your model, your theory about how the CMB is explained, how the creation of the light elements is done in this model, and how you find that this model is very much better than that it resolves all the problems which the existing concordance model has, and there's no need for concordance model then.
Well, that's more than one question. But anyway, let me start with the question of expansion versus the linear relationship of redshift and the redshift and distance. We started this work almost 20 years ago in response to the early findings of the Hubble telescope about the size of objects. I had raised somewhat speculatively in a paper in the 1990s that there was some evidence that the true relationship of angular size with redshift was simply 1/z. And there was some preliminary data that indicated that. But it wasn't until the Hubble Space Telescope did reveal what the angular diameters were at high redshift, up to a redshift of 5, that we really had evidence for this relationship. And I basically looked back at the Tolman test. So the Tolman test was developed almost as soon as there was a Big Bang hypothesis, in which Dr. Tolman said, well, if the universe is expanding, we get this strange phenomenon in which the angular size of objects does not continue to decrease with increasing distance.
Yes.
Because at high redshift, these objects were closer to us when they emitted the light than they are now. So you get the paradox that these objects would start to expand on the sky even as they were more distant. And the contrary prediction, if the universe is not expanding, we have the very simple prediction that surface brightness does not change. So the surface brightness of an object is its apparent brightness divided by its apparent size on the sky. And of course, we know here on Earth, if we move a light twice as far away, its apparent brightness will go down by 2 squared, a factor of 4. Its angular size will go down by a factor of 2. Its area will go down by 2 squared, 4. You divide these, it will always come out the same. So that was a very striking prediction that we rapidly found was exactly confirmed by the HST data. And this is as Tolman said, is a clear-cut case test of all theories that involve expansion. If you have that the Hubble relationship is due, even in part, to expansion, then you have this peculiar curve of angular size, and the surface brightness declines very steeply. It declines with the cube of 1 plus the redshift. So when you get out to redshifts of 5, you're talking about a difference of a factor of 125 or something like that. So what the model that we're developing simply excludes expansion. The surface brightness test is a clear-cut yes-no test for expansion. And as far as I can see, and we will be publishing, as I say, JWST completely confirms the Hubble that expansion cannot fit this data. No form of expansion can fit this data. So there's no hybridization that I can see of expansion and non-expansion. It's one or the other. Now, just briefly on these other topics, which we've been covering at great length in this video series, the basic phenomenon that the Big Bang theory attempts to explain by this unique, uncaused creation of the universe can be explained using the phenomena that are known here on Earth, which is gravitation, electromagnetism, the behavior of plasmas, which is based on ultimately on electromagnetic theory, and nuclear reactions. So to take one example, and this was not an original idea with me, it was developed by others. I put more meat on it. The question of the light elements. We have a lot of light elements in the universe. 1/4 of the mass of the universe is helium, which is a light element. That's attributed to the Big Bang. in the Big Bang Theory. But we know that stars like our sun are at this very second producing vast amounts of helium by nuclear fusion. The same nuclear fusion that my company is trying to develop for here on Earth. Not this exact same reaction, a different one. So if we apply plasma physics plus gravitation to the question of the formation of galaxies, we can derive and check with observations at all scales in the laboratory a model in which, in the early stages of galactic formation, the stars that are formed tend to be very large, fast-burning stars. So to review for the audience, it's well known that the more massive a star is, the faster it burns its fuel and the shorter its lifetime. So theoretically, we derived, again, straightforwardly from well-known physical laws, that these early stars would have to produce a great deal of helium and very little else, because they weren't big enough. They weren't the biggest stars. They weren't big enough to explode as supernova. And it's supernova that basically produce all the elements heavier than helium and distribute them to the universe, such as the carbon, nitrogen, and oxygen that make up a lot of our matter. So these theories produced a lot of predictions for the abundance of helium, lithium, and deuterium, which could be checked. And they check out very well. In contrast, the predictions of the Big Bang Theory predict too much helium compared with the least helium we see in stars, and 20 times too much lithium. So the production of light elements occurs in the history of individual galaxies. Second of all, we know from our experiments here on Earth, and we've seen this in many phenomena in the universe up to the scale of quasars, that purely electromagnetic phenomena coming out of the contraction of objects from stars up to quasars create accelerated beams of energy. These are beams of protons in one direction, ions in one direction, electrons in the other. As these self-contained beams, which are also called filaments, move out into the universe, they become the source for scattering cosmic microwave background. The energy of the cosmic microwave background comes very naturally from the question of the formation of the light elements. We have so much helium, we have an observed amount of helium in the universe. And if you calculate how much thermonuclear energy was released in the production of that helium, you get almost exactly the amount of energy that's in the cosmic microwave background. Again, this is something that was not noted first by me. It was noted way back, pretty soon after the discovery of the cosmic microwave background. So first of all, you can predict, knowing only the density of matter in the universe, the temperature of the microwave background, which was not correctly predicted by the Big Bang. Something that is sort of covered up in history, but is nonetheless true. Predictions prior to the discovery of the microwave background were approximately 10,000 times off. They were 10,000 times too much energy. So that's where the energy comes from. we see observationally that most of that energy released in early galaxies gets thermalized by dust down to very far infrared radiation. With the filaments that emerge from these energetic objects, that's scattered further and thermalized down to the 2.7 K degree radiation that we observed. And there was a key test between these two hypotheses, which back in the 1990s, Dr. Tully actually suggested to me, which was, if we look out in the local universe, this hypothesis that the microwave background is scattered by a radio fog implies that radio radiation cannot travel through the universe as freely as optical radiation or near infrared, that it gets scattered. And there is a test for that. We look at very nearby galaxies and galaxies that are somewhat further away, but not far enough to have significantly be at an earlier stage of their evolution. And what do we find? We find that systematically, the further away they get, the lower the radio radiation is compared with the optical or near infrared. If the microwave background originated at great distances exclusively and was not being produced by scattering in the local universe, there would be a shield, there would be a filtering of that radiation, and it would not have a black body spectrum. It would have what would be called a gray body spectrum. So basically, observations pretty much rule out that the microwave background could have purely originated at extremely high redshift in a Big Bang. It must, at least in part, be originating in this radio fog. So we don't have the capability yet, because we don't have the funding for it, to test whether you can get all of the aspects that we observe of the CMB, its extreme smoothness and so on, from this hypothesis. But we do know observationally that the origin of the CMB in a Big Bang doesn't fit the data. So that's a very long answer to multiple-barreled question. So I'll turn it back to you.
Right, thank you. But I think you yourself said your theory can at least partly explain the microwave background observation. And what is the other part, you would think, that was missing part? Is only part?
No, what I'm saying is that out of this non-Big Bang but evolving model, the energy in the CMB is correctly predicted. Second of all, we correctly predict that if there is a radio fog of these filaments scattering radio waves, thermalizing them, then radio radiation must drop faster with distance than optical or near infrared. So those are two predictions that are clearly correct. What we have not done, which would take detailed modeling, is say, okay, assume that all of the microwave background is coming from the radiation of the galaxies as they form in the universe, including in the local universe. Can we predict that, that the smoothness of the radiation background is 1 part in 100,000? can we predict the actual distribution of anisotropies? And the answer is no, not so far, because nobody has, that takes considerable computer resources and considerable time resources to create such modeling. And the funding for that is simply not available.
Yeah. And I think that automatically then answers the baryonic acoustic oscillation power spectrum in the CMB as well as in the matter distribution, like galaxies correlation, distance correlation function, which is pretty well verified according to the claims of the concordance model.
Well, the baryon, the problem with the concordance model and its accord with observation is it isn't predictions, it's purely fitting. You have a model that has more than a dozen free variables. I mean, they talk about a 6, 7, or 8 variable model. But if you read the papers, that simply ignores several other things, nuisance variables, decisions that they've made in their modeling that are actually free variables that are adjusted to fit the data. And as was famously stated, you know, with 5 variables, you can fit an elephant, and with 6 variables, you can make it wiggle its trunk. It's meaningless. As long as you were continuously changing the model to fit pre-existing observations, fitting those predictions, for example, to the wave-like differences in density that we observe in the universe, it's meaningless. Many phenomena produce wave-like oscillations. Plasma phenomena produce wave-like oscillations. You do not need a Big Bang to produce wave-like oscillations. And to say, oh, our theory predicts these wave-like oscillations very well, when there's still discrepancies after the 8th or 9th variable, that's not science. That's not the scientific method. The scientific method is about comparing predictions made before observations and testing theories with new observations. Every time the Big Bang theory has been tested, it's wrong. And they have to add a new epicycle, dark energy, dark matter. We see this phenomenon going on right now, in which these predictions about the size and age of galaxies that appear to be older than the Big Bang, you know, immediately they have new hypotheses. I was watching a NASA conference sponsored by the Space Telescope Institute, in which they were discussing the recent data from JWST. Most of the presentations were observational. So they were just saying, hey, these are the observations. Gee, it looks like they don't fit theory, but we don't care, we're not theorists. But there was one theorist there, and he showed theoretical predictions of the abundance of these very massive galaxies at very high redshift. And he showed that indeed the predictions that had been made prior to JWST were wrong by a factor of 10,000. That is, they were predicting 10,000 fewer of these galaxies. And he said, but in fact, if we just change one free variable, which was a variable he called the stochasticity, the randomness of the model, we can fit the data very well. And, you know, in an instant, you saw the curves jump upwards by a factor of 10,000. Well, of course, a theory that can predict anything in a range of 10,000 predicts precisely nothing. it is useless. I've made the analogy, maybe people are sick of hearing it, but I think it is relevant, that the difference between the scientific method and the Ptolemaic method that most of cosmology uses is the difference between getting on an aircraft and being assured that knowledge of aerodynamic engineering assures you that you'll get safely to the other side of the Atlantic, and getting on an airline that has crashed 16 out of 17 times, but each time they can explain why they crashed. I don't think any of us would get on that second airline. It's definitely time to get off of that second airline. So that's why we don't.
But then it comes to that if that is the kind of modeling we have in cosmology, whatever we do that we can explain one way or the other, or some make predictions which are good, some not, what's the use of doing cosmology anyway? And what is the benefit of it? When people have asked me this question, what is the use of the work you are doing on Earth? So I think this is a very relevant question for a lot of audience, that they want to know what benefit it has when you have so much uncertainty in this kind of thing, which is not very scientific. And even if you are able to develop it scientifically, what is going to be its use? Except burning money to create toys, 10 billion toys to put in the satellite and try to do some more observations.
Right. Well, I think that is the key question. If you use this Ptolemaic method of making observations, making theories that fit the observations, having the predictions of the theory contradicted, do the cycle again, that is not going to produce anything of use to people here on Earth, because it isn't the scientific method. It is the method that Ptolemy used centuries ago, and it has been revived. And the person who taught me so much about scientific method, Dr. Hannes Alfvén, who was the originator of this general approach to cosmology, for years, he pointed this out, that cosmology was leaving the scientific method behind, starting back in the 1960s and the 1970s with inflation, with dark energy, with dark matter. But if we abandon that approach and say, cosmology is not different from other sciences, that we have to use the approach of using things that we can test in the laboratory. And our laboratory today is as big as the solar system because we can send our instruments all over the solar system. If we can make predictions based on theories we can test in the laboratory, and we can use the cosmos as a laboratory and derive from what we observe there models of how matter and energy behave here on Earth, then we can actually produce fusion energy. I mean, in our own work, we have used, and again, this is work that was pioneered by Hannes Alfvén and his colleagues, we have used the study of the plasma phenomena that we can study very easily in the universe, especially in our own sun, where we're very close to the sun, and the time scale of events on the sun are very convenient, minutes, seconds, hours. Those same phenomena, production of these dense filaments, production of plasmoids that concentrate the energy even further. These are the exact phenomena that we're using in our work to produce fusion energy in the laboratory, and which other fusion researchers have had to take into account, because this process of filamentation occurs in practically all fusion devices. You know, you go back in history and the big debates around geocentric and heliocentric, which were finally resolved first by Kepler's laws, and then by Newton and others' discovery of the law of gravitation. That ended up having a huge practical effect. Because if you can accurately predict position of the moon in the sky, you have a clock. And if you have a clock and you can observe where the sun is on your sky, then you know your longitude. If you know your longitude, you can get safely from one side of the ocean to the other, which was very risky before that. So what we do in cosmology has a great impact, in my opinion, on what we do on Earth if we abandon the Ptolemaic method and we return to the scientific method that has proven its utility to human beings in so many other fields.
Yes, that's definitely a very good answer for it. Yeah. There could be a lot more questions, but I don't want to really take more time asking.
All right. Well, why don't we're 5 minutes early, so why don't we open it up to questions from the audience? But if more questions occur to you, you still have 5 minutes left. So if people want to, let me see, how are we going to do this? Okay, do people have questions in the chat? That's the best way, I think, is people could put questions in the chat.
I'd like to see the chat.
I'm sorry I can't answer your question about how you stay awake at 2 a.m. We did this with the best time that we could for the maximum population, but we can't cover all 24 hours. Okay, I don't see actual questions. Does anyone have a question? You can just speak up because we're a small group.
I have a question. So we can use the raised hand function too.
Well, the problem is if we're both on screen, I can't see your raised hands. So just speak out. We don't have a mob here.
So I am curious when you talked about the coupling constant varying in terms of doing this, if they all vary together, but what if the coupling constants themselves are varying with time, such as increasing with time or decreasing with time? Did you have a model of the varying?
Yes. There's a model for its variation, and we found that it is the model, what we know, the model itself does not say whether it should be varying, constant, or not varying at all, So what we do, we take the model and fit some data, observations like supernovae data. And that then provides us how these constants vary. Because there is one single function which is determining the variation of all these constants, and there's only one constant in that function which needs to be determined by this fitting. And we found that these constants are decreasing with time. They had higher values in the past and lower values now.
Would an exponential decreasing model work? Because that's actually what I predicted.
Yes, this is exponential, right? But it is exponential not in the way that it will keep increasing indefinitely. It increases at certain rate and then becomes constant.
But if they started off big and are exponentially increasing towards zero, so very, very small. So you look at something like the Planck's constant, right? And if that was very big in the beginning of the universe and now is at its present value and just slightly decreasing.
Actually, what it is that it had some value in the past and And the way it is, if you see the formula of that, is the exponential function is not the exponential increasing or decreasing. It is modulated by a factor which makes it reach a constant value in the past. And current value is what we know is the current value.
Just briefly, but if the gravitational constant was varying, wouldn't that have an observational effect on the evolution of the sun, which is explained with a constant gravitational constant, and even on the Earth, in which our model of the evolution of the Earth has assumed that the mass of the Earth hasn't changed. The gravitational mass of the Earth hasn't changed.
Yeah, it would have, provided it's the only one which is varying. If other constants are also varying, the speed of light, and distance is measured with the speed of light, that is also has to be changed accordingly, then you find these things cancel out. In fact, I have to yet to design an experiment, and I have visited the NIST, for example, in the USA, and so many other places, people, and discussed it, and we couldn't find an experiment which we can design to determine the variation of these constants when they are varying in a co-varying way, which we have predicted, not individually varying. Yes, you are right. If they are individually varying, the speed of light remains constant, but only g is varying, then you are right. Then it should be observed.
So what observations, cosmological or otherwise, would test your theory? How does your theory make predictions that can be tested by further observations?
This is where the challenge comes in, that we are trying to find a cosmological or terrestrial observation where such variation can be tested, because in everything I have tried to look into, they cancel each other, happily cancel each other. And initially, I thought there will be some effect on for Chandrasekhar mass, for example, or Boltzmann, not in the Stephen Boltzmann constant or something. But in all of these, I find when they are used in the measurement, then the cancellation happens.
Mm-hmm. All right, we have something in the chat. I'm going to have to lean forward to read this. If the universe is not steady state but evolving, wouldn't that imply entropy was lower in the past? Therefore, if you run time back far enough, you get to very low entropy state, like what it would be in a singularity, which is predicted back before the Big Bang. Good question. Okay, so if we turn the clock back to the early origins of the idea of an origin of the universe, we get back into thermodynamics. Because what happened in the late part of the 19th century, the early part of the 20th century, is that Boltzmann, who had developed the theory of thermodynamics, basically said, well, my theory says that all systems must move towards the state of equilibrium. The state of equilibrium, without using the term entropy, is the state at which energy flows cancel, that there's zero net energy flow from one part of space to the other. And he said that thermodynamics determined that systems left to themselves move towards thermal equilibrium. So that, obviously, Boltzmann and everybody else realized that begs the question, well, but the universe and ourselves are very far from equilibrium. How did that occur? And that became a big problem. So one of the ways that that was resolved was the idea that the universe must have been created at a finite point in the past. And initially, it was the idea of not a Big Bang, but a random fluctuation. But basically, the universe was sitting around for an infinite amount of time, and in an infinite amount of time, anything could happen, even something as unlikely as a low entropy, very well ordered, very high energy flow state, and we're sort of devolving back from that. At the time these speculations were all occurring, along came Lemaitre and the idea of a Big Bang. And Eddington, who was one of the people talking about thermodynamics, said, here's the solution. The universe originated, presumably by some not natural phenomena, at a high state of energy, huge energy flows, low entropy, and boom, that solves the problem. To make a long story short, people weren't very satisfied with this solution because it sort of made inexplicable the evolution of life on Earth, because life is not a short-term phenomenon, even in cosmic scale. For billions of years, the Earth has been developing larger and larger energy flows within the biosphere. It has been moving further and further away from equilibrium. And of course, you can say, oh, well, we have
upstairs.
sun as a source of energy. The fact is, it doesn't matter. The thermodynamic principles that Boltzmann derived, any system, including a sun-Earth system, should move towards equilibrium. Well, again, it's a long story, but which is described in my book, The Big Bang Never Happened. But Ilya Prigogine in the 1960s, who had been looking at this problem for a long time, said, well, the problem is Boltzmann's thermodynamics are a special case. They apply only to systems that are already very close to equilibrium. They happen to be the systems most engineers are interested in. But they're not the general case. The general case in which you have systems that are far from equilibrium, there are tendencies for them to move further from equilibrium. And that the notion that the convenient mathematical concept of entropy has to be defined in specific cases in such a way that entropy always increases. And the increase of entropy does not lead, in the general case, towards equilibrium. It does not lead towards disorder. It does not lead towards lower energy flows. It leads actually in the opposite direction, towards greater energy flows. So that's what's happening in the universe. I'm going to be starting a series, I hope soon, depending on my own time, in which we're describing the actual, what we know of the actual evolution of the universe, which has observationally been going in the direction from lesser energy flows to greater energy flows, from closer to equilibrium to further from equilibrium. Okay. Another question. Or comment. We've still got.
There are a few questions here.
Do you want to jump in with another question, Dr. Gupta?
Actually, there was one question about the. I think we.
You're looking at the chat.
Yeah, I'm looking at the chat. Yeah, but I think it might be better if somebody has question which we have not answered. Maybe just speak up. That might be easier because reading the chat takes time.
Anybody else with a question or comment? Well, all right. I mean,
There had been a comment earlier asking for a definition of tired light, that at least some people were not familiar with what was being referred to and how this operates. It's hard finding it in the chat because that's the way chat is just hard to find.
Yeah, so I could answer it if you like.
go ahead.
Tired light is really, in the case of tired light, the energy loss is proportional, or energy loss of a photon is proportional to the energy of the photon itself and the distance traveled. And when you write it mathematically, it gives you the kind of relationship, logarithmic relationship with Eric discuss. That's as simple as that.
Right. But I would, as I say, I would define tired light more broadly as any phenomena that causes photons to lose energy with distance. So, there is no reason to hypothesize a priori an exponential relationship, because we're dealing with a process that we do not know the origin of at this present time. Now, this doesn't have to be as fuzzy-wuzzy as dark energy or dark matter, because we have the capability of studying this phenomenon in our own solar system. Satellites that have not been launched but could be launched in the near future have the sensitivity in which we put satellites up several million kilometers apart from each other. And we actually have instruments that are sensitive enough to measure whether the light is redshifting between them. If it is redshifting between them, that would be a clear experimental test that tired light phenomenon does exist, whatever its formula is. Because in the expanding universe concept, expansion only occurs in systems that are non-gravitationally bound. There's never been a hypothesis that the solar system is expanding. So if we see a redshift between very sensitive satellites, that would be a clear-cut test that there is tired light. But it wouldn't be a test of the exact formula. As I said, tired light as a general phenomenon could have a linear relationship with distance, logarithmic or whatnot.
Actually, I have proposed one experiment I should mention about it that might be somewhat easier to see, because if you have gravitational lensing of quasars at high redshift, and these images then, because they travel, the gravitational lensing creates multiple images of an object, and each image is due to the distance traveled, which is different from the other one. So that way you can have the travel difference, time difference between these images. Creation could be of the order of months or up to a year or sometime longer. So that means there will be, if there's a tired light effect, it will give you a different redshift in different images. And if it is a hybrid effect, then you should be able, if you're 2 or 3 images or more, you can be able to isolate that. How much is.
But this would be differences in the redshift in parts per billion.
But that will be even worse in the case of satellites only. You will be even.
Well, but the difference is, in the case of satellites, we have the capability on Earth, and we can put them in satellites, to measure time differences at frequency differences that are of the order of 10 to the minus 17. So if you take 10 to the minus 17 and apply the Hubble relationship, you can get differences that could be measured to high accuracy in only months to a year with the sort of technology we already have, if we put it in satellites like the proposed LISA array. but measuring an actual wavelength to a part per billion coming from a astronomical source, that's going to be very difficult because you're measuring something that's a fraction of the width of the line width. With man-made lasers, we can make the line width very insignificant. I mean, we can make lasers that have line widths of 1 hertz out of frequency of 10 to the 14th hertz.
I think you're right.
Doing it with a natural phenomena is a lot more difficult than doing it with an artificial instrument.
Actually, it was suggested similar experiment for one of the things, the redshift. How the redshift itself evolves with time was suggested by Geraint Lewis. And I was just following up. If he can measure that, then it can be measured.
But again, you have to make so many assumptions about the that the line itself does not have any internal structure. It's not varying. You're talking about, fuzzy natural phenomena that are much more difficult to measure to parts per billion than artificial phenomena where we can make them precise. But since we are running out of time, one last question, Dr. Rajendra, is, don't you think, though, that if further measurements on this angular size do come out much lower than your predictions, isn't that a possible contradiction? I mean, isn't the angle, isn't a full statistical treatment of these angular dimensions, comparing galaxies with the same intrinsic luminosity or the same mass to each other, isn't that, in the long run, a clear test of these different models, because they have radically different numerical predictions?
I think that's something that's very interesting. You are saying one of the problem is that angular diameter depends on the size. Angular size depends on the physical size. Now, we don't know. I have assumed certain physical size of the galaxies to determine these angular sizes at different redshifts. But really, even the physical sizes could be quite different. And unless we know what the physical sizes are, it is very difficult to say what their angular sizes would be in any model. So I think there will still be so much uncertainty. And as you said, we have to do some stochastic determination to really see whether...
Right, of course, we do have to do the statistics. But the prediction of the non-expansion is that since the physics of galaxy formation doesn't really change, and we're looking in all cases at young galaxies, the ones that are brightest in the ultraviolet, that the physical size of the galaxies for a given luminosity should remain the same. So that's, again, a prediction that has no wiggle room, no free variables. And I think that we will be doing that test in the very near future. But we are running out of time, so I do want to thank Rajendra Gupta for coming and having this dialogue. This is the sort of dialogue that should be happening all through the cosmological community, but generally isn't. And I want to remind people that the second in this series of dialogues will be occurring just in 6 days' time on October 17th with Dr. Silas Lapini, who has been studying for a long time the largest scale structures in the universe. So,
can I make one comment? Last comment.
Sure, last comment. Go ahead.
Yeah, I should have said when the audience asked me about question about exponential behavior of the constant. No, it is exponential function comes in there, but really ultimately the function behaves asymptotically. It approaches an asymptotic value at high redshifts.
Going back in time.
Back in time, yeah. At
But
high redshifts,
Going
it-
forward in time, it's exponential.
Yeah, that's right. Yeah.
Okay, thanks for that clarification, and hopefully we'll see many of you next week.
Okay,
Take
thank
care.
you very much for on this kind of gathering dialogue.
Well, thanks for coming.
So, bye-bye now.
Bye. The knowledge of plasma that we gain from studying the universe helps us to achieve fusion energy in this decade. If you want a fast transition to a clean environment and a higher standard of living, fund LPPFusion's research. The link's in the description. Share, subscribe, and get new knowledge of the cosmos at the same time.